today, the reason why casinos and insurance companies are still in business, of course, I'm actually going to explain that to you, the connection between the law of large number and why casinos and insurance are in business. Okay, so let's get started. I need you to pay attention to what I'm displaying right now. I want to start with the law of large numbers. Law of large numbers. You know, if you take a look at, let me just tell you our intention here. The belief is that we may not be able to quantify or predict the behavior of a single value of a random variable, but we believe that we can predict, the averages, okay, over time. The averages over time become stable and predictable compared to when you have a single value. Of course, I'm actually going to explain that, how it affects insurance business and how it affects casinos. Now, I wanted to take a look at what I'm actually displaying now. Okay, I said let y1, y up to yn be IID. IID means identically and independently distributed. Okay, with mean mu and the standard deviation sigma. Of course, at the beginning of the semester, of course, I walk you through all of that. Whenever you have random variable, whenever you have something that varies, we can actually figure out the average. The mean is the average. We can also compute the standard deviation. Now, I said here, let y bar n be the associated sample mean. Okay, then for any epsilon greater than 0, okay, epsilon here maybe is more or less like an error or like a gap. Okay, for any epsilon greater than 0, okay, when I take the limit as n tends to infinity, okay, when I take the limit as n tends to infinity, the probability of the absolute value difference between the sample mean and the true value. When you take a look at this guy, that is a population mean. We also call that true value. Okay? We call that population mean or true value of mean. True value of mean. There's a difference between this guy, okay, and this guy. Okay, this guy here is just the sample mean. So we're trying to say sample mean converges to population mean in probability. That's exactly what we're trying to say. Let me tell you this. If I want to know the average, the average amount a student of this class spend in a week, okay, if I want to figure out, or let me just go in general. If I want to know the average amount students of this university, okay, spend in a week, okay, to be able to get that average directly, it means I need to investigate or question or interrogate every student in the university. But you know what? If I do that, of course, I will be able to get population mean, the true mean. But why is it that I cannot do that? I cannot do that because I'm limited by budget and resources. Whenever we want to conduct research, the reason why, instead of us to study everybody in the population, we normally take a sample, okay, because we're limited by budget. We're limited by budget. So because of that, I'm not able to get the population mean directly. But when I take it, what I'm going to do at the end of the day is to take a sample, take a sample of individuals from such population, okay, when provided the sample size is large, okay, we expect the sample mean to converge to population mean. That is exactly what we're trying to say here. We're trying to say as n tends to infinity means as n becomes infinitely large, we expect the probability of the absolute difference between the sample mean and the population mean to be less or equal to epsilon. You know that epsilon is a very small value. It's like a very close to 0, and that we occur with probability 1. Okay, that will occur. So this is trying to say the convergence is going to take place between the sample mean and the population mean when you are working with a sufficiently large sample. Okay, so that is exactly what we mean generally by the law of large number. Now, when we're talking about law of large number, we have two types of law of large number. We have the weak law, we have the strong law. Please pay attention. Okay, for those of you that are just coming in, I'm taking attendance, and the purpose of the attendance is to give 4 extra credits to students who have been actively involved, like coming to class regularly, okay, and you need to, there's a list going around, make sure you put on your name. At the end of the semester, you're going to advise me on how you want to spend your extra credits. You may advise that, okay, put my extra credit on the final, I'm actually going to put that. Or put my extra credit on assignment, or whatever, because it's your extra credit, you earn it. So you're going to advise me on how you want to spend that. Okay, so I was talking about, law of large number. There are two types of law of large number. We have a weak law of large number, and we have a strong law. Now, let me explain what we mean by weak law. Now, if you take a look at this, I said, suppose y1, yn are identically and independently distributed random variable, each with a defined and a finite mean of these. Under this condition, the WLLN states that the sample average of this n random variable converges in probability to mu. What am I trying to say here? It said, individual value may be random, may be unpredictable, but averages over many events. Go ahead.
We kind of already know that, unlike variance, expectation is not kind of affected by the dependence, right?
Can you say that again?
Unlike variance, expectation is not really affected by dependence, right?
No, when we talk about expectation, expectation here is trying to say, I have a certain value intact, like as a student now, you are expecting to get, your expectation is to pass with A in this class. That's your expectation, right? Okay. Now, you can have expectation for me. You can also have expectation for variance. I can have expectation for standard deviation. The other times I'll be like, okay, maybe I want the variance to be, this is what I'm expecting for variance to be, or this is what I'm expecting for standard deviation to be, or this is what I'm expecting my parameter to be. Expectation work on anything depending on your intention. So it doesn't really matter whether I'm talking about independent or dependent. Of course, in this class, we talk about conditional expectation. So, a conditional expectation is talking about, I'm talking about expectation for dependence. So as far as expectation is concerned, we can use it for dependent, we can use it for independent. Does that make sense? Mm-hmm. Which now depends on what you want. But what I'm describing here is, okay, let's bring casino in. Okay, the reason why casino is still in business is because of the law of large number. They rely, when individual play a game, okay, individual outcome, casino may not be able to predict an individual outcome because individual may lose or win. But what casino is going to make casino to have an edge at the end of the day? Casino will make an edge at the end of the day when they have millions of followers, those who players playing the game. Because even though individual random variable, y1, y2 is like individual person playing casino, which those who are playing games are independent, right? the fact that I win does not mean you're going to win. That is what we mean by independence, right? Okay, the players are independent. We're not able to figure how, the outcome of individual player, but we can actually figure how the averages. Does that make sense? Because on the long run, if thousands, if millions of players play, okay, casino will actually have an edge at the end of the day. Which means, what do I mean having an edge? Please pay attention now. If this is what a casino is targeting, meal. Do you see what it's targeting? Casino is targeting this. Okay? But this guy here, okay, is what is the sample averages, is average that occur over several events. Okay? Now, that will converge in probability to mu. So, which means, there's a high likelihood. Let me put it this way. What is the meaning of this very P here? It means convergence is taking place between sample mean and population mean in probability. In probability means if casino has so many players, okay, there is high likelihood that the sample mean converges to the population mean. What is the population mean? That is the expected profit for casino. And that is why the expected profit for casino, okay, expected profit, okay, for casino, they are expecting it to be greater than what? 0. When the expected profit is greater than 0, it means house wins. Casino wins. Go ahead.
I think I'm a bit still confused why. So the sum of expectation is not is not affected by dependence, right?
The sum of expectation. What do you mean by sum of expectation?
So you're saying that yi is basically an expectation right there.
No. This is not expectation. This is sample mean. This one is just a regular way of finding the average. How do you find average in statistics? You do what? You sum the observation and divide by n. That is a sample mean. So the sample mean is different from population mean. The population mean is the true value of mean, is what you are expecting. Okay? There's a difference between what you are expecting and what happened in reality. Now, you want a student want performance now to converge to become what you have in mind. What you are, I want A in this class. Okay? Then you are now working hard, even though midterm 1 maybe doesn't yield to A, midterm 2, but maybe you need enough space of time to get A. That enough space of time is what we mean by n tends to infinity. But for casino, okay, it means I have millions of players playing, because casino will only be profitable if there's a lot of players playing, because at the end of the day, their expectation will be greater, their expected profit will be greater than 0, okay, which means house will win if so many players are involved. So the bottom line here is they may not be able to predict the outcome of individual player in advance. The outcome of individual player could be, individual may win or lose. But at the end of the day, when there are so many players involved, of course, the casino will win. Because if they are not winning, why are they still in business? They rely on the law of large number. Another one that I'm actually going to talk about is insurance. Insurance sell policy, maybe like the accident, the acts, and so on, the property damage, and so on, like that. How do you think insurance sets the premium? If insurance only have few policy holders, they are never going to be profitable. Okay? An event of one person on those events, for one person is unpredictable, but they can predict the events of so many. When so many people are involved, average is involved. You can't find average without so many individuals. So what I'm trying to say is that the insurance company, will be able to predict what the profit is going to be. If they can't predict profit, they cannot set premium price. They can't set premium. So they set premium ahead of time because they look into the behavior of so many of their policy holders. And let me tell you this, in insurance, the YI will represent loss. What do I mean by loss? Loss is if there's a claim. Whenever an insured person make a claim, it's a loss to the insurance company. So even though they may not be able to predict the risk of each individual, but when so many individuals, millions of individuals are involved, they can have it predictable. Now, what am I trying to say? Average allow us to predict under uncertainty compared to individual value. That is the power of the average. Does that make sense now? And that's exactly what I'm trying to say. Please pay attention to this. To this. Now, this guy is saying, this is the average that you have over so many events. And this is the average you are anticipating. This is what you get as average at the end of the day when n tends to infinity, when the number of policy holders become sufficiently large, then the sample mean that you observe converges to the population mean. And that is exactly, now, I need you to pay attention to this. Pay attention. Look at this. What is the meaning of this? Now, I want to explain that. What is the meaning of this? You know, the other time, we said we can write this guy in two ways. Another way that I can write that, please pay attention. Okay, pay attention. Another way I can write that, I can write limit n tends to infinity. Okay, the probability of xn minus mu, okay, less than epsilon equal to 1. You see that? If I put less than here, this is going to be 1. If I put greater or equal to, that would be 0. You know, this guy equal to 0 means the probability that convergence will not take place. Okay? The probability that convergence will not take place is 0. Then it means convergence can take place. Does that make sense? That's what you see here. So this is the absolute difference between your expectation and observed. Observed is in terms of sample mean. Okay, observed is sample mean. Now you are trying to say, and this guy is the epsilon, very small value. Okay, this guy is the epsilon, though it is greater than 0. Okay, because you know why? We don't say epsilon equal to 0. If you say epsilon equal to 0, then we are saying sample mean is exactly the same as population mean. It's never going to happen. Sample mean cannot give you exactly the same as population mean. Let me tell you this. In science in general, in the scientific community in general, or let me just say, if we're using perspective of modeling, a model give approximate to reality. If you want to use a model on reality, model does not give us exact characterization of reality. Otherwise, that model will be perfect. No model is perfect. So we don't say this equal to this. Here, we don't say sample mean equal to population mean. We say it converges to population mean in probability. In probability means there is high likelihood that the sample mean converges to population mean when n is sufficiently large. N tends to infinity means n is sufficiently large. Does that make sense? Now, this is what we call the weak law of large numbers. Let's talk about the strong law. Please pay attention. We have a weak law of large number. We have a strong law. How is a strong law different from weak law? I'm actually going to explain. the two of them still talking about convergence. But strong law does not mean convergence in probability. It means convergence almost surely. Almost surely, like very close to one, almost surely. This is what happens. If I want to find sample mean, I'll first start with the sum. Please pay attention. I sum, okay? Maybe here I'm summing, maybe Y high is a loss or is a claim, okay, by policyholder. And I want to know the total claim. This is the sum. Now, if this is the total claim, this is the average, right? This is the sample average of claim. Maybe I'm talking about fire claim or talking about accident claim or medical claim or whatever, if you take a look at this. Now, this guy now converges to the expected value, the expected loss that insurance is, what insurance is expecting, because insurance is expecting this to be a loss. So this guy converges to that, or AS means almost surely. Almost surely means as n tends to infinity, okay, the sample mean is equal. The sample mean equal to that occur with probability 1. When something occurs with probability 1, okay, it means it's almost surely. But what is the difference between this guy and this guy? Please pay attention. What is the difference between this and the weak law? The weak law, please pay attention. The weak law is saying the convergence is within a threshold. The strong law does not say it's within a threshold. Okay? The weak law, that's why it's called weak law. It says, our sample mean converges to population mean, okay, if the probability of the absolute difference between the two is within a threshold, okay? Within a threshold, less than epsilon, that probability equal to 1, okay? And here, greater or equal to epsilon, that probability equal to 0. This guy means for every epsilon greater than 0. So this is a weak law. With a weak law, okay, the convergence is not almost surely with a weak law. The convergence is within a threshold, and that's why you see the absolute value of the difference lie within a threshold. But in the case of a strong law, the convergence is not within a threshold. Go ahead.
Is epsilon related to the sample size?
Okay, epsilon is not related to this, but epsilon is something very small, but it's not 0. It's like us to say, there's going to be a gap. The gap is not going to be much. Does that make sense? Okay. And in some situation, there's possibility the epsilon may be connected to sample size because, you're right, because when the sample size is small, the epsilon is going to be greater, it's going to be so large. You are very correct. Because what is dictate, send me a message for extra credit. You have 1 point, that means plus that one, that will be 5 points for you. Because let's see this. Take a look at this. If I have small sample, the epsilon is actually going to be a little bit large because epsilon is the gap. We do not want gap to be much. We want gap to be very, very small. Even though the gap is not going to be 0, but that will depend on the sample size. And that's why in statistics, we normally encourage large sample. Even though we don't want to study, we do not have resources to study everybody in the population, but we normally encourage investigators to take a large sample. Now, you now see the difference between the two. So whenever you put AS, it means almost surely. There is nothing that is surely. Even in the strong law, we say almost surely. Does that make sense? So nothing is sure in a stochastic environment. Now, we want to work on this now. Suppose y1 up to yn, IID, whether it may be a PDF or a PMF with mean mu and a standard deviation sigma. Okay, let's say we're able to get our sample mean, right? If you take a look at, give me 1 second. if they take a look at this, let me see this.
Can I ask you a question?
Okay, go ahead.
So that omega in SLLN, is it something related to the measure space you mentioned?
Yeah,
earlier?
it's something, because if you take a look at this, the omega here lies in a measurable space, like,
Which triplet was it?
huh?
Which triplet was it?
Because when at the beginning of this class, we talk about possibility. So that omega is like possibility, maybe possible values of random variable that you are investigating on. So, and that is why this guy, Sn is the mean. That mean is come from this possibility, from the sample space. Okay? So that is what we mean. So when you have before we can actually define a random variable, of course, we have a sample space. We normally start from sample space. So sample space is a collection of possibility. So it now depends, maybe do you want to talk about possibility of insurance claim? Maybe insurance claim going from 0 to $1 million, or it now depends on this possibility. Now will be set by the company or by a particular entity. So it's just like, you are talking about this is the range and domain. You remember in high school, the domain. What is the possible values of S? That's exactly what we mean.
So since we're touching every set, every element in the sample space.
Exactly.
That's the reason why it's not a threshold, and that's the reason why it's strong, right?
No, that's not the reason why it's strong. The reason why it is strong is because it converges almost surely to that. That is why it is strong. Not because you touch, even in the other one, in the weak, you touch as well. You know why you touch as well? Because the fact that your n is infinity, n tends to infinity, you're touching a lot. Mm-hmm. The sample size is what determines. If you look at the two, whether weak law or strong law, you're touching almost everything. Does that make sense?
So we can use epsilon delta to kind of explain strong law?
No.
No.
The reason, the absolute value, I like that question. The absolute value comes in when, okay, now, does it make sense to say, what is the probability of the absolute difference less than 0? We are always going to, this guy is always going to be a positive, okay? I can find the probability of the absolute difference between two things greater than 5, or less than 5, or less than 3. You understand what I mean? So when the probability of the absolute difference is involved, then that's a convergence in probability.
It has to do with absolute value.
Exactly. And it has to be within a threshold. The threshold is the epsilon. Do you know the question I'm expecting? There's no epsilon here. No epsilon means no threshold. You see that on the long law? Do you see that epsilon? But there's epsilon here. Epsilon is okay, if different exists, the difference shouldn't be more than this. More than a particular value, but not 0. You understand what I mean? So that is just the difference. Okay, now coming here now. I want us to say the power of mean. Okay, if I actually have a y1 up to yn, it's a random variable, and each of these identically and independently distributed. Okay, independently distributed means they have the same distribution. Okay, probability distribution. And I know the sample mean is z. This is the sample mean. Okay, now, do you know the meaning of this? That guy means theoretically, in statistics, expected value of sample mean is population mean. Do you know where that happens? We normally say sample mean is unbiased estimator. Because we're using sample mean to estimate the population mean. Our intention is to get the population mean. But what is the only way to get the population mean? If I carry out 100% enumeration. We do not have resources for that, to study everybody in the population. What do we normally do? We take a sample. When we take a sample, the mean of the sample, the mean that we got from the sample, will represent the population mean. And what we normally do is It's not as if the sample mean is the same as population mean, but you know what this guy is trying to say? On average, sample mean
Is that because
equal
of the
population
weak
mean.
law, or is that because of the strong law?
Is that what?
The unbiasedness, is that because of the weak law, or is it because of the strong law?
That's a very good question. The unbiased is said because of anything, either strong law or weak law. So our belief is that, let me do this. Our belief is this. Give me 1 second. I think I want to. Okay, take a look at this. Let me explain what that guy is talking about. What do we have in the parentheses? That is the sample mean, right? Now, do you know I'm trying to tell the world here? Sample mean also varies. How? How can sample mean varies? Now, if I ask you to conduct a research, go to the University of Minnesota. Each of you should select 50 students randomly. When you select 50 students randomly, maybe get information about the amount they spend weekly on food. Okay? Now, do you know that your average will be different from its average, will be different from your average? Why is the average different? Can someone tell me, why is the average different? Why is everybody's average not going to be the same? Let me say that again. I asked you to choose 50 students randomly. You know what I mean by randomly? Okay, choose 50 students randomly. Get information about how much they spend every week on food. Then, each of them will spend differently. You now find the average, right? When she finds the average over 50, you find the average, the average will not be the same. Why? Let me start from you. Variance. Variance of what? Sampling variation. That is it. And that is why when you listen to news, there are some media that normally predict the likely winner in the election. If you listen to maybe CNN, the CNN will say, okay, 70% to this candidate. If you go to another news network, it's going to be a different value. Why? Because that is sampling variation, just like what you said. Because of that, the sample mean, the one in the parentheses, is a random variable. And when it is a random variable, do you know how we can know the truth? We will find the average of the averages. You have average, you have average. If I have 1,000 investigators, there will be 1,000 averages. Then what am I going to do? I will find the average of the averages. That is what this guy is trying to say. He's saying the average of the averages is going to give us what we want. It will give us the true value of the mean. Does that make sense now? That is what we mean. So on expected value of y bar equal to mu means, on average, the sample mean, become population mean. But how can this occur? At times, it now depends on the distribution you are choosing from. Please pay attention. When I choose Y1, if you guys are choosing from normal distribution, then this average is going to converge to that very mu. But if you are not choosing from normal distribution, before the expectation of y bar become mu, then your sample size has to be extremely large. Let me tell you this. Whether you are if you are choosing any sample size, whether small, moderate, or large from population, and the population is normal, there's no problem. Does that make sense? That is always going to happen. But situation where the population is not normal, then before you can achieve normality, before that guy is going to happen, then you may actually need a large sufficient sample size. We're coming back to that. That's what we call central limit theorem. Okay? So here, I'm trying to say expected value of y bar equal to that. Now, do you know that if I have expected value of yi itself is average, is mu, expected value of y bar, also mu. Expected value of what from individual observation is average. Expected value of y bar is also mu. But you know what? What is the variance of yi? The variance of yi is sigma squared. But what is the variance? What is the variance of y bar? The variance of y bar is sigma squared over n. So out of this and this, which one do you think has a lower variance? Is it for individual or for the mean? Which one has a lower variance? Can somebody tell me? N here is the sample size. Which one do you think has a lower variance? Go ahead. The mean. Thank you. Because the only condition under which this and this will be equal is when I only investigate one person where n equal to 1. Can a researcher just investigate one person? No. He has to investigate more than one person. So the moment you investigate more than one person, the variance of the mean will be lower than the variance of individual. And that is the reason why in statistics we normally focus on average. Can you see that? And that's exactly what I'm saying. Now, the moment, if you take a look at what I'm trying to talk about here, 1 second. Now, if you take a look at here, if the variance of y bar equal to that, then the standard deviation of y bar will be the square root of this, which is this guy. Can you see that? But the standard deviation of y, don't forget, if variance of y, the standard deviation of y is sigma. But the standard deviation of y bar is sigma divided by root n. The standard deviation of y bar is what we also call standard error. Do you know what this guy measures? This guy measures variability around sample means, when sample mean become random variable. But this guy measures variability around individual observation. There's a difference between variability around individual observation and variability around the mean. The variability around the mean is what happened the other time when I said each of you have different means. If each of you have different means, we can find the mean of that, of the means. We can also find the standard deviation of the means. Because mean becomes a random variable. So the deviation around the mean is called standard error. In statistics, we use standard error a lot. Does that make sense? Okay, so that is exactly, so this guy here is a standard error. The standard deviation of the mean is standard error. Now, how does it really apply? How does the law of large number apply generally? Please pay attention. I'm still going to use this material. Now, take a look at this. Law of large number for every epsilon greater than 0. Go ahead.
Is the variance then a biased estimator since the variance of the mean is different than the variance of...
Okay. You said, is the variance a biased estimator or not? Okay. Actually, if you are going for 5102, the next chapter you're going to start in the textbook is what you just told me right now. Now, expected value of this, okay, we have it to be that, okay, and we also have situation where it is not that. So the sample variance can be biased. It can also be unbiased. Okay, does that make sense? But there's something that is going to happen. It can be asymptotically unbiased. You know what they call asymptotically? Maybe it is biased at a small sample, but when the sample is large, it becomes unbiased. Does that make sense? Okay. Now, take a look at this. I said for large, if you're using the law of large number for every epsilon greater than 0, we said this the other time. We said this is a convergence in probability, right? If you take a look at that, the probability that absolute value difference between the sample mean and the mean and the population mean will be less than epsilon equal to 1. Okay, so that's what I said. And I said, if f of s is a PDF of a norma, now, let's say, for instance, you're sampling from a norma. This is going to hold all the time. Where, you know what that guy is saying? He said, sample average follow normal distribution with the mean of that, and this is the variance. You know, we said it. The variance of sample mean is sigma squared over n. So if you are working with a normal distribution, irregardless of your sample size, okay, the sample may follow normal. I'm going to say this again. If Y1, Y2, if individual Y follow normal, automatically the Y bar will follow normal. Does that make sense? Irrespective of the sample size. But what of in the situation? Take a look at this. Can we say more about distribution of Y bar in the absence of normality? That is what I'm going to do next. What I'm going to do next, I will demonstrate to this class. If you are sampling from non-normal population, okay, and there's no normality, how can you achieve normality with a sample mean? That is now going to take us to central limit theorem. We know what central limit theorem says? Central limit theorem says, okay, I pick this guy from non-normal population. This guy came from non-normal population, non-normal population, non-normal population, non-normal population. Then their average will only follow normal if I choose a sufficiently large sample of them. If I did not choose a sufficiently large sample of them, their sample mean will not follow normal. Does that make sense? And how can we do that? That can be achieved through central limit theorem. So what you're going to hear from me next time, the question is, how large is the large? How am I going to know if, even though they are not coming from normal population, and I want the sample mean to converge to, I want the distribution of the sample mean computed from that to follow normal distribution, how large should the sample be? And we normally, central limit theorem, put that at least 30. The sample size has to be at least 30. Okay, that's what we're going to do next. Okay, the bottom line, let me quickly walk you through. Let me, have a recap on what we've done today. Today, I introduced you to central limit theorem, even though we haven't really done central limit theorem. We started with the law of large number. There are two types of law of large number. We have a weak law, and then we have a strong law. Okay, and we're focusing on how convergence can take place between the sample mean and the population mean when the sample size becomes infinitely large. Okay, and I try to say for the convergence, for probability convergence that we call the weak law, is when the probability of the absolute difference between the sample mean and the population mean is less than an epsilon. Epsilon is a positive number, it's not zero, okay, if that probability equal to 1. So all what I'm trying to say is that the likelihood of the convergence taking place between the sample mean and the population mean, okay, is actually very high, okay, when the sample size become infinitely large. That's what we call probability convergence, that we also call the weak law of large number. And I said for strong law of large number, the strong law of large number is not a probabilistic convergence, it's a convergence almost surely. Okay, we are very sure that convergence is actually going to take place provided sufficiently large sample is taken. And I also demonstrated the practical application. And I said the reason why casino and insurance are in business is because they rely on the law of large number. Even though when individual play a casino game, it could win or lose. Do you know that a casino cannot even predict ahead of the time whether a particular player is going to win or not? But there is something casino can predict ahead of time. They can predict averages. Because when we have averages over so many events, of course they use the power of the average, for them to be able to know whether they're going to win. Because casino will always win. They may not win on the short run, but they're actually going to win on the long run. And the only way they can win on the long run if there are so many players involved. So they benefit, from the law of, and look at that, law of large number. Large number is talking about sample size, being large. That's what it means. Okay. Then I think I also talk about why insurance, why, the way because they have expected profit loss, and, the loss to insurance is when the individual has a claim, even though individual behave, individual insured person is a random variable. They may not be able to predict whether a particular individual is going to come up with a claim, but you know what? Collectively, they can actually benefit, use the power of average, to be able to know how the loss, the average sample loss will converge to the expected loss. Because if they don't know the expected loss ahead of time, there is no way they will decide on the premium. There's no way they're going to decide on that. They are still in business because they are profitable, okay? And they are profitable because they are using statistical law of large numbers. And that's why they are in business. So what I'm going to walk you through next is, okay, if I'm sampling from a distribution, and the distribution is normal, because the probability distribution of the population you are sampling from matters. For instance, if I have identified a population distribution to be normal, and irrespective of the sample size that I take, whether small or large, the mean will follow normal distribution. But what if in a situation where I'm sampling from gamma distribution, or I'm sampling from exponential distribution, or I'm sampling